Hi, my name is Michael Chun, and today we're going to go over the Machine Learning Coursera course, Logistic Regression Lab. We're going to implement logistic regression and apply it to two different datasets. First, we're going to run our packages, numpy, matplotlib, and utils. So first, we're going to build a logistic regression model to predict whether a student gets admitted into a university. So first, we're going to load our dataset into xtrain and ytrain from this file path. Then we're going to view our variables. And so this prints out the first 5 elements in xtrain. This is exam 1 score, and this is the exam 2 score. And the type of xtrain is a numpy.nd array, or an array. And the first values of ytrain are 0, 0, 0, 1, 1. And so 0 means that the student was not admitted to university, and 1 means that the student was. And again, it's a numpy.nd array. And we can also check the dimensions of our variables. So this tells us that we have 100 training examples. And so it's a good idea to visualize our data. So we can plot our data, and we can see that there is already a pattern emerging. There is like a linear line. Now we're going to implement the sigmoid function. The sigmoid function is g of z is equal to 1 over 1 plus e to the negative z. So we're going to take in z, which is a scalar numpy array, and return g. So we can set g equal to 1 divided by 1 plus, and there's a function in numpy that calculates this e to the negative z for us, which is exp. And we're going to return g. And all tests passed. Cost function for logistic regression. The cost function takes this form where we do the sum of all of our losses and divided by m. And so the loss function looks like this. And notice how it takes in FWB. So we're going to fill out this compute cost function, which takes in x, y, w, and b, and returns the total cost. So we already have the variables m and n, which are the rows and columns of the x, and total cost will initially be 0. And we're going to first iterate through our function for I in range of m. We're going to sum all of our losses, so the total cost will be equal to the total cost plus our loss. And our loss is going to be this term over here, and I'll type it out. So notice how we take in FWB, which is our prediction, which is equal to g of wx plus b, or our sigmoid function. So we can say that FWB is equal to sigmoid of z. And z is equal to wx plus b, or numpy dot xi and w plus b. And when we're done with this, we are going to divide by m. So total cost is equal to total cost divided by m. And all tests passed. Gradient for logistic regression. We're going to implement this algorithm for the gradient descent algorithm. Notice we have partial j, partial b, and we're going to abbreviate it as djdb, and do the same for djdw. So we're asked to fill out this function, which takes in x, y, w, and b. And we have m and n as a shape, dj, dw over here, and dj, db. I've copy-pasted the FWB at every single I example from above because we're going to use it over here. Notice that the FWB is inside of these two terms, the djdb and djdw. And furthermore, FWB minus y is inside both of these terms. So we're going to call that error. So error is simply going to be FWB minus y bracket I, which is yi. Then we can iterate through n training examples, or n features for j in range of n, and calculate this term on the bottom. So dj dw at j is going to be equal to dj dw j plus this error term times xij. And dj db is equal to dj db plus the error. And we have to remember to divide by m. And all tests passed. Learning parameters using gradient descent. This applies the gradient descent algorithm and plots the cost function for us. Notice that as we increase the number of iterations, the cost function decreases. And we also notice that the cost function did most of the decreasing at around 1000 iterations. Applying the decision boundary, we use a helper function to help us do this, and we see that it has separated the data pretty well. We can see how well our model predicts our training set, and we will implement the predict function. So our predict function will produce 1 or 0 based on the prediction that we already have. And we'll use this following heuristic. So if our prediction is closer to 1, if it's greater than or equal to 0.5, we will predict a 1. And if it's closer to 0, so that means if it's less than 0.5, we will predict a 0. So I have xwb, m and n, mp, and for each training example, we will get the prediction from above, so this code's from above, and we'll very simply say if FWB is greater than or equal to 0.5, we will predict a 1. Else, we'll predict a 0. All tests passed. And we can see that our training accuracy is 92%, which is pretty good. While feature mapping allows us to build a more expressive classifier, or it is also more susceptible to overfitting. So we're going to implement regularized logistic regression and combat this overfitting problem. So the only difference here is we have this regularization term. And so we're going to calculate that with compute cost reg, which takes in x, y, wb, and lambda. So for j in range of n, we're going to compute the sigma over here. We're going to say reg cost equal to reg cost plus this wj squared term over here. And then we're going to set reg cost equal to reg cost divided by 2m times lambda. And we have our expected results. Grading for logistic regression. Now we're going to implement the gradient for regularized logistic regression. So again, it looks complicated, but we are simply adding the regularization term. And in this case, we're going to do it for dj dw. So I have the same parameters as just above of m and n, dj db and dj dw. And so we are modifying dj dw by iterating through j. So for j in range of n, we're setting dj dw at j to be dj dw j plus this lambda over m times wj. And all tests passed. Learning parameters using gradient descent. So we are applying the algorithm again, and we can see the cost function going down with the number of iterations again. And we notice it's taking a while because it is a non-vectorized version. And then afterwards, we're going to plot the decision boundary. And we see the model has fitted the data. And we can also evaluate our regularized logistic regression model and see that there's an 82.2% training accuracy. And we're done.